Hello viewer and welcome to the e-learning classroom. So today we want to look at a summary of gas laws. This is a topic in Form 3. Gas laws is also a topic in Physics Paper 1. So in today's video we'll focus on the equation of state, and then we'll also be able to look at the three laws, that is Boyle's law, Charles' law, and also the pressure law, and we'll understand the in-depth knowledge on the scientific concept and ideas that are required for this particular topic. So first of all, it's important to understand that gas laws only apply for an ideal gas. Gas laws only apply for an ideal gas, and an ideal gas is a gas that obeys gas laws. An ideal gas is a gas that obeys gas laws. So in this equation of state, let's look at what we have here. First of all, if you factor out volume and temperature, so that one is Charles' law. Volume and temperature is Charles' law. You can call it TV, Charles' law. Then if you factor out pressure and temperature, this one is pressure law. If you factor out pressure and temperature, you get pressure law. And finally, if you factor out pressure and volume, this one gives you Boyle's law. That is PV. Boyle's law PV. Charles is TV. Then pressure law is PT. So maybe we can start with the Boyle's law. So for Boyle's, we are relating pressure and volume. So for that, let's consider a balloon. When you reduce the volume of a balloon having some air, so you realize that this balloon normally bursts. If you compress a balloon full of air, the balloon normally bursts, and that means the pressure has increased. Or a vehicle tire full of the tube full of air. If you compress that tire for some time, you realize that that tire will burst. Essentially, it means when you're compressing a balloon full of air, the pressure increases, and that's why it bursts. In other words, pressure is inversely proportional to volume, because we are reducing volume and pressure is increasing. So that means pressure is inversely proportional to volume. If you remove the proportion sign, it means pressure is equals K all over V. You introduce a constant to remove the proportion sign, and that means if you multiply by V both sides, PV is K, a constant. In other words, pressure times volume is a constant. Pressure multiplied by volume is a constant, and that simply means pressure 1 volume 1 is equal to pressure 2 volume 2, and that's a continuous formula, because a constant simply implies that if you multiply pressure by volume at any point, you get a constant value. If you multiply pressure by volume, you should get a constant value. So with that now, that is a summary. That is a summary of the formula. This formula for Boyle's law. We can also look at the formula. We can also look at the formula for Charles' law. We are going to look at the graphs later. Formula for Charles. So let's say we have a balloon full of air. And then for Charles, we are relating volume and temperature. If you increase the temperature of that air, or if you heat that balloon, the volume will increase. That means pressure, that means volume is directly proportional to temperature. Because when you increase the temperature of the balloon is expanding. In other words, the volume of that balloon is increasing, meaning they are directly proportional. If you remove the proportion sign, you introduce a constant. So volume equals kT. If you divide both sides by T, volume all over temperature is a constant. Volume over temperature is a constant, and that simply means volume 1 all over temperature 1 is equals to volume 2 all over temperature 2. Volume 1 all over temperature 1 equals volume 2 all over temperature 2. That is a continuous formula, because we are saying if you divide volume by temperature, you get a constant, a number, a fixed number. Lastly, pressure law. Pressure, we are relating pressure and the temperature. Pressure and temperature. So let's say we have a balloon whose volume is fixed. But for that balloon now, you are increasing the temperature and the volume is constant. That means the pressure of that balloon will increase. So essentially this means that pressure is directly proportional to temperature when volume is constant. And that means pressure is equal to kT. If you divide by T both sides, pressure all over temperature is a constant. Meaning when you divide pressure by temperature, you get a constant number, and that simply means pressure 1 all over temperature 1 is equal to pressure 2 all over temperature 2. It's a continuous formula, simply implying that anytime you divide pressure by the temperature that is giving you that pressure, you get a fixed number. So that is how we get the equation of state. We are getting the equation of state by combining all those components now. So that's how we get now the equation of state, by combining all those components. So with that now, before we look at these setups we have here, let's consider now the graphs. So we can start with the Boyles law. Let's start with Charles. Where they are directly proportional. So let's look at the two graphs we have here. Let's look at the graphs we have here. Simple graphs, just a sketch of the graphs so that you can understand exactly what we are saying. So we have volume is directly proportional to temperature. So that means volume in centimeters cubed. Against temperature in Kelvin. We also have volume in centimeters cubed against temperature in degrees Celsius. We also, let's start with these two. So we are saying volume is directly proportional to absolute temperature, meaning the graph there is a straight line passing through the origin. In other words, as we increase the volume, the temperature, volume is also increasing. Volume against temperature in degrees Celsius. So 0 Kelvin is also known as absolute zero temperature, and it is equal to negative 273 degrees Celsius. So that means in degrees, the graph will look like this in degrees. Let's see how the graph looks like in degrees Celsius. So this value here is negative 273 degrees Celsius. So the graph is a straight line with a positive gradient, but it will pass all the way to negative 273. Let's look at now pressure against temperature. For pressure law, we know pressure is directly proportional to absolute temperature. So that means we have pressure in pascals against temperature in Kelvin. Because they are directly proportional, it simply implies that the graph is a straight line passing through the origin and with also a positive gradient, meaning the two are directly proportional. And then we also have the same for degrees Celsius. So pressure in pascals, temperature in degrees Celsius. So this one will also pass through negative 273. That means the graph is a straight line. If you prolong this graph, it is passing through a point here, which is negative 273 degrees Celsius. That's how you draw the graph of Charles and the graph of pressure law, meaning those graphs are simply telling you that they are directly proportional. They are directly proportional from what we have looked at. Let's look at the Boyles law, the graphs. These ones are inversely proportional, so we can draw the three graphs. Let's draw three graphs for this case. The first one, the second one, and the third one. In this time now we have three graphs. We have three graphs for this case. Let's see how they appear, they turn out. So the first graph we are going to draw is a pressure in pascals against the volume in centimeters cubed. So we have seen pressure is inversely proportional to volume, and that means the graph is a curve which goes like this. That is the curve we have. That means as you are reducing volume, pressure is increasing. As you are reducing volume, pressure is increasing, is rising. But remember, for this particular graph, volume is not going to zero. In other words, the volume is not reducing up to zero. It's almost zero, but not zero. And the reason for that is that when you compress air, some gas, the gas normally liquefies. The reason why you cannot reduce volume of a gas to zero is that after reducing the volume up to some value, that gas will normally liquefy. In other words, it will now become a liquid. And we know liquids are incompressible. That's why you realize this volume is not going up to zero. The curve is not touching zero, but it is almost zero, but not touching zero. Because when you reduce the volume, when you reduce the volume of a gas, at some point it becomes a liquid, hence liquids are incompressible. Let's look at the same graph now, pressure against reciprocal of volume, pressure against 1 over volume. So if you look at this, pressure is directly proportional to 1 over V. That's when you take 1 over V to be one thing. You are now working with 1 over V as one component, and the two are directly proportional. But if you take volume alone, it is inversely proportional. That's why the graph is a curve. But if you take pressure and 1 over V as one component, 1 over V being one component, then that graph is a straight line with a positive gradient, showing that the two are directly proportional. If you take 1 over V to be one component, the two are directly proportional. Lastly, we have a graph of PV against P. That is pressure times volume against pressure. And this graph is a constant. So that's a graph which is horizontal, meaning there is no slope there. So that is the general overview of the 3 laws: Boyle's law, Charles' law, and pressure law. We are saying for Boyle's, pressure is inversely proportional to volume. That means when you compress a balloon, pressure increases, and that's why the balloon bursts. Then Charles' law, volume is directly proportional to temperature. That means when you compress a balloon, when you increase the temperature of a balloon, volume will increase because the balloon will expand. The air in the balloon will expand. Then pressure law, pressure is directly proportional to temperature, meaning when you hit the balloon full of air at constant volume, pressure will increase. So with this now, I want us first of all to look at these 3 setups. We have the setup of Boyle's law, the setup of Charles' law, and the setup of pressure law. These are applications. Maybe you can, I can have something for this to distinguish them from the other work. You can have something to distinguish them from the other work here. So we can look at them directly. Let's see. So let's see now how we can see them. These 3 diagrams are very, very important because they are highly examinable in paper 1. So let's start by looking at this one here. Let me also make this one a bit distinct so that you can understand exactly what we are saying. Let's make this one more distinct also for the sake of clarity and the neatness of the work we are doing here, so that you can see exactly what we are doing. So maybe we can look at Boyle's law for this particular setup. So first of all, we have pressure gauge. Then we have gas coming from the tap, meaning this gas is pushing the oil up on this side, but our interest is this air which is trapped here, because in Boyle's law, we are relating pressure and volume. So our interest is volume of the trapped gas here and also the pressure of the gas. Remember, pressure of this side must be equal to the pressure of this side for the liquid not to move, because if the liquid is moving towards the pressure gauge, then pressure of the trapped air is more. But if the liquid is rising towards the trapped air, pressure on the pressure gauge is higher than this side. So that means essentially pressure of this side, which is the pressure from the gas pump, which you are reading on the pressure gauge, is equal to the pressure of the trapped air here. And that simply means we are relating the two. So first of all, what are the measurements? Measurements that can be taken. So the measurements that can be taken. So first of all, we have the pressure. You can take a measurement of pressure of the trapped gas here by reading the pressure gauge. You can also take a measurement of height of trapped air corresponding to volume. In other words, the height of this trapped air here is also the volume of the air. We also take it to be the volume of the air. What factors are held constant? Factors held constant. So the factors held constant for this experiment. First of all, because when you are stating the law, you say that pressure of a fixed mass. So that means the first constant value is always the mass of the gas. Because we normally say pressure of a fixed mass of a gas is inversely proportional to its volume, provided that temperature is kept constant, so mass is fixed. The other constant value here, because we are relating pressure and volume, it means temperature is also constant. That is the room temperature. The temperature is also constant. Those are the two fixed values for this experiment. Then for this experiment, maybe we can consider how can we use this setup to illustrate Boyle's law? How can we use this setup to illustrate the Boyle's law? How we can use this setup to illustrate Boyle's law? So the first thing, maybe you can say how the setup can verify Boyle's law. So always the first thing or the first point is to take the initial readings of pressure. Take the initial readings of pressure and volume. You take the initial readings of what is the value of pressure gauge, the reading, and the volume of the trapped air, which is also the height. After taking the initial reading, what you do now, you adjust the pressure from the tap. We have a tap here. So you adjust the pressure. Adjust the pressure and take more readings. You adjust the pressure and take more readings of pressure and volume. You adjust the reading here, the pressure from the gas tap, and then you take more readings of pressure and they are corresponding. They are corresponding values of volume. In other words, you are reading more values of pressure and volume. Then the third point is plot a graph of pressure against reciprocal of volume. A graph of pressure against 1 over V. Then you must also tell us how the graph looks like. So the graph, if you look at the graph here, it is a curve whose tangent has a negative slope, and this shows that number 4, because we are verifying, shows that pressure of a fixed mass of a gas is inversely proportional to the volume, provided that temperature is kept constant. So that is how the setup can be used to verify Boyle's law. You take initial readings, adjust the pressure from the tap as you take more readings of pressure and corresponding values of volume, plot a graph of pressure against 1 over V. Then you tell us how the graph looks like. The graph is a curve with whose tangent has a negative slope, showing that pressure of a fixed mass of a gas is inversely proportional to a volume, provided that temperature is kept constant. Let's look at this other setup here for Charles. So you can see what we have. We have a thermometer here. We have sulfuric acid index and trapped air. We have a meter rule. They are held together through a rubber band. They are held together with a rubber band. And then we have hot water here. We have source of heat and the stirrer. So first of all, let's look at purpose of. Let's start with the measurements. Which measurements can you take from this experiment? So of course the first measurement is temperature of gas. Let's say just temperature. We can take the measurement of temperature. that is through the thermometer. We can also take the measurement of height of trapped air, which also corresponds to volume. In other words, that height, we are taking it to be the volume. So those are the two measurements. We can take the measurement of height of this trapped air in the test tube and also the temperature reading from the thermometer. Then factors held constant again. Factors held constant. So the factors held constant, one is always the mass of the gas, that is a trapped gas, mass of the gas. And the other factor that is held constant here, because you are relating volume and temperature, is now the pressure. Because you are doing it, the pressure of the pressure is balanced because you're doing it at the normal atmospheric pressure. Then, before we go to how it can be used to verify the Charles law, we can also look at function of stirrer. What is the essence of the stirrer? The stirrer we have here. So the stirrer stirs the liquid for uniform heat distribution. So it stirs the liquid. You can use it to stir the liquid to ensure uniform heat distribution. Then the second last, we also have purpose of sulfuric acid index. What is the purpose of this sulfuric acid index? So it has two functions. First, if you look at the index here, it is trapping the air. So that means it traps air. It is trapping the air. The other thing, it dries the air. Dries the air. That air that has been trapped, sulfuric acid acts as a drying agent. Then the next point, it acts as a pointer on scale. It acts as a pointer. It acts as a pointer. You can be able to read the height of the trapped air by using the sulfuric acid index as the pointer on the scale. Then with that, we can also look at how can this setup here be used to verify Charles' law? How can this setup be used to verify the Charles' law? How can this setup be used to verify the Charles' law? So the first thing, you take the initial reading of temperature and volume of dry air. Remember, that is always the first point. Take the initial reading of temperature and also the volume of dry air, or the height of dry air corresponding to volume. After taking the initial reading, the second step is heat the liquid as you stir. You can see the stirrer. Heat the liquid as you stir and measure more values of temperature and their corresponding values of volume. Heat the liquid as you stir and record more values of temperature and their corresponding values of volume. Then plot a graph of volume against absolute temperature. So the graph is a straight line passing through the origin. It's a straight line passing through the origin and with a positive gradient. Remember, we know the gradient is positive when the right hand here is above the left hand here. The graph is like this. Right hand is above the left hand, so it has a positive gradient showing that Volume over fixed mass of a gas is directly proportional to absolute temperature at constant pressure. So lastly, we can look at now the pressure law. Pressure law. So we have the setup here for pressure law. So you can see we have some pressure gauge, we have a thermometer, we have pressure gauge, we have a thermometer, we have some heat, source of heat, water bath. We have some water bath here, and then we have the setup as you can see. You have the clear setup as you can see from here. So and the first question, two measurements that can be taken. So you can start with that, the measurements. So the measurements that can be taken, one of course is the temperature, because you can see the thermometer, temperature. The other measurement is pressure. Pressure can be recorded because you can see the pressure gauge. Then factors held constant. Factors held constant. So there are two again. One, of course, is the mass. Mass of the gas. Mass of the gas is held constant. The other one, because we are relating pressure and temperature, is volume. Volume of the gas. Remember, our interest is this gas here, the trapped gas here. The trapped gas here. Then with this setup now, maybe we can look at how the setup can verify pressure law. How the setup can verify pressure law. So the first point, you take the readings of, take initial reading. You take the initial readings of pressure and temperature. You take the initial readings of pressure, that's from the pressure gauge, and also the temperature from the thermometer. Then number two, heat the water bath. Heat the water bath and record more values of pressure and temperature. You heat the water bath and record more values of pressure and temperature. Then number three, plot a graph of pressure against temperature. Plot a graph of pressure against temperature. You must also tell us how the graph looks like. So if you look at the graph, it is a straight line with a positive gradient, because the right hand is above the left hand. Is a straight line with a positive gradient and passing through the origin. Then because you are verifying a law, you can also tell us what does that mean. So this shows that pressure of a fixed mass of gas. This shows that pressure of a fixed mass of gas is directly proportional to absolute temperature, at constant volume. Pressure of a fixed mass of a gas is directly proportional to absolute temperature at constant volume, because the two are directly proportional. As one increases, the other one is also increasing. So before we finalize, we can look at now the assumptions in gas laws. The assumptions in gas laws.